Hello everyone. Uh, Welcome to the Learn Competitive Programming with Code Chef channel. Today we are going to learn about modular exponentiation. So what is modular exponentiation? It is the next part of modular arithmetic. Yesterday I took a free class on modular arithmetic on the Unacademy platform. So if you're not familiar with the modular arithmetic basics like addition, subtraction, and multiplication, you can go and view the basics class I took on an academy. It's free currently. Also, if you're not sure about the modular arithmetic basics, you can still follow this class because the modular arithmetic basics which I uh, teached yesterday were really basics and really easy. So I think you can still follow this class if you don't know much about modular arithmetic, right? So today I'm going to teach about modular exponentiation. This is going to be one of the class that I took in the number 3 course of my course in the competitive programming program at Unacademy, right? So a little introduction about myself. I'm Nishchay Manwani. You guys might know me as Zeusors at codeforces.com, where I'm an international grandmaster, currently all India rank 3. Or guys might know me as NM at codechef.com, where I'm all India rank 12 and currently a 7-star programmer. Or you might guys might know me as other competitive contests as well, like Kickstarter, Core Jam. I have also participated in those. And recently, I've joined as an educator at an academy. This is my profile at NM, right? So I have taken one course, which is of number theory, and I'm going to take my next course. I decided to take this free class in between on modular exponentiation. So what I wanted to introduce you about the competitive programming program at an academy, right? You might have heard about that. So what does that offer? It offers live interactive classes. All of the classes would be interactive completely. You can ask me doubts. I will be answering them. I will be asking you questions and you have to answer them, right? There would always be relevant problems at CodeChef, which I have selected personally for my course number 3. I've selected some problems and gave a list to each of the learners so that they can, after each class, they can go to this uh, um, code chef and practice the problems that I have selected. Also, you will get a doubt support from me. Also, I have a Discord server where you can ask me doubts personally if you are one of my learner in my course. Or there are many teaching assistants at an academy as well, which are all very talented. So you can ask them doubts as well. Currently, there is also a teaching assistant in the YouTube chat. So if you would like to ask any doubt, he would be answering your doubts, right? So all of the educators are really talented in computer programming. All of them have a really strong background in computer programming, right? There are people who have gone to ICPC World Finals. There are people who have won IOM medals. There are people who have high rating in Code versus Code Chef like me. And then there are people who have worked in big companies like Google, Flipkart, the dream companies which we talk about, right? So these are all the educators. You might have heard the names: Tanuj Khattar, ACM ICPC World Finals 2017-2018; Himanshu Singh, Hitman on Code Forces. He's also a world finalist. Deepak Kaur, world finalist. Murgappan, he is a software engineer at Google. Arjun, he is a IOM bronze medalist in 2015. There's Pulkit Chabra, coder Pulkit C, right, on Code Forces. He's also 2246, a master on Code Forces. And then there is me. And all of these people are really talented in competitive programming. All of the teaching assistants are also really talented. So in this program of competitive programming, we are going to have some topics. So we have categorized them as completely basics, which are uh, basics of programming, not even competitive programming. So you can go to them if you don't know anything about programming, which is introduction to programming, C++ foundation, Java foundation, etc. Intermediate, which is like the basics of competitive programming, STL, number theory, basic data structure, recursion, DP, etc. And then there is the advanced stuff, which can be considered as a intermediate or advanced part of competitive programming, like segment trees, graphs, advanced dynamic programming, etc. Like, and then there is a miscellaneous course as well. Uh, Himanshu is taking this course of ICPC regionals plus world finals problem solving. So he would be solving the problems which have come in the past world finals and regionals. Also, there is another course on lost uh, algorithms in competitive programming. I'm looking forward to that course because that includes algorithms like parallel binary search, binary lifting, uh, problems that come rarely, but when they do come, you can't solve the problem uh, from any other algorithm than that algorithm, right? So there are many courses which would help you during your competitive programming journey, right? So these are all the courses. Most of them are currently coming to fruition, and they're going to be the next set of courses coming up. So this is the forum where you can ask your doubts to teaching assistants on me on CodeChef. This is the platform where I will be putting out the questions, the list of questions where you can solve on number theory if you have a course on number theory, or graphs if you have a course on graphs, right? So the pricing for this all would be for the first month it was 1,000 rupees per month, and for the subsequent there is 4,000 per month for if you selected the 6 months option, or 12 months. If you selected the 12 months option, you would get 2,500. So to avail these options, you have to type in the referral code, which is capital E small n capital E small m. This is a referral code NM, which is my username. So you can just type in this referral code and you will get these discounts onto the subscription, right? So with this is the introduction to the Unacademy program that I wanted to give. Let's go to the topic at hand, which is modular exponentiation, right? So let me just share my screen to my whiteboard, and we'll study about what is modular exponentiation, right? So modular exponentiation, you might have know what is exponentiation, right? Exponentiation is just x to the power y. Something example, we have 3 to the power 3, which is 27, right? Easy. What is modular? Modular means we have to find something in the modulo operation, modulo some m, right? So let's say we have 12 modulo 5. So what is modulo? Modulo is the remainder when we divide 12 by 5. So when we divide 12 by 5, we get the remainder as 2. So this is going to be 2, right? So what modular exponentiation basically means, it means that we have some x to the power y, and we have to calculate that modulo m, right? It's as simple as that. We just have to calculate x to the power y modulo some m. But why am I teaching this as a separate concept? Because it is really necessary to for you to understand why are we why is this important and why is this used so much. So the first point that I wanted to make is, if you are trying to find, let's say, 10 to the power 10 to the 10 to the power 10 to the power 100. So this is going to have 100 digits, right? All of them would be zero, but let's take some other example where all of the digits are not zero. Let's take 11 to the power 100, right? So this is going to have more than 100 digits for sure, and all of them might not be zero. So to get this number would be a lengthy task, to get 11 to the power 100, because it is going to have 100 digits. Even in programming languages, if the number of digits are more, it is the calculations are going to be more extensive, and it is going to take much more time rather than computing a short number. When we in C++, when we do operations in int or long, the operations are taking very short time, right? We can multiply two numbers in a very short time, we can add two numbers in very short time. But when the number of digits is around 100 digits or 10 to the power 5 digits, these operations take much more time than when it takes if we are doing just an int or long, right? Even in Python, when the number of digits in a number is short, it takes less time, and if the number of digits is greater, then it takes larger time. That is why we want to calculate this x to the power y, some small number. M is going to be some small number which is going to fit in the int range. Let's say it has 9 digits, right? So it is going to be a really short number, small number. So we can calculate x to the power y modulo m and do not have to worry about, oh, is it going to fit in an int? Is it going to fit in long? Is the operations time going to be very large? We don't have to worry about that. We just have to calculate x to the power y modulo some small number, right? This is the first use. Let me write that here. uh, that we don't have to worry about the number of digits, right? And the second point, to understand why am I teaching modular exponentiation as a concept, to understand the second point, we have to first try to understand how do we find this modular exponentiation, right? How do we find some x to the power y modulo m? So uh, I would be telling you the second point around the middle of the lecture, right? So before that, I want to, for the people that have joined in and might have some doubts in this lecture. So I'm going to just specify that I'm going to take all of the doubts at the end of the lecture, right? So if you do have some doubts, just keep them ready or just keep them in the chat. At the end of the lecture, I'm going to go through the doubts and answer those doubts if I can. Also, the teaching assistants in the chat will be answering your doubts in the middle if they can, right? So let's, before that, let's try to devise up an algorithm, right? That we have to find, we are given three numbers, which are x, y, and m, and we have to calculate x to the power y modulo m, right? We have to calculate this. It's a really simple concept, but what you can do is you can either go the inefficient way or you can go the efficient way. So the inefficient way, which is a naive version, right? Naive method is to generate an answer. Currently, we have an answer here, answer, which is going to be 1 initially, right? And each time, then we are going to have a loop for I in, for I from 1 to y. We're going to have a loop from 1 to y. And each time, we're going to update answer as answer into x modulo m. So taking the modulo operation at each step ensures that we don't have to worry about the number of digits. And we are taking the modulo operation at each step, right? And just doing answer is answer into x. So after the first iteration, it's going to become x to the power 1. After the second iteration, it's going to become x to the power 2. After the yth iteration, it's going to become x to the power y, modulo m each time, right? So then we'll just print the answer. There's a naive algorithm that we can think of. But if you try to find out what is the space and time complexity, right? Space complexity, it's easy. We are just initializing one more number. So the space complexity is going to be space complexity is bigger of 1, right? But the time complexity, because we are iterating from 1 to y, so the time complexity is going to be big O of y, right? And this is the naive method in which you can do exponentiation. This actually is a nice algorithm if y is really small, right? If y is, let's say, less than equal to 10, right? Then you can do this. But if y is greater than 10, then there is a really improved version of this algorithm which you would want to apply, which is called, which is in repeated squaring paradigm. So we have something called, which is repeated squaring paradigm. And you might be afraid of this term because this is a big term, but this is nothing but just a type of algorithms, right? And the algorithm that I'm going to show you next of modular exponentiation is an example of an algorithm in repeated squaring paradigm, right? So do not worry about the name here. I'm just written the name so that you can maybe remember that and try to understand what do I mean by repeated squaring, right? So the idea here, the algorithm, the improved version, efficient algorithm, is going to be just we're just going to analyze what is x to the power y in two cases. First case, y is odd, 1, y is odd, y is even. Let's take the even part first, right? The first case is when y is even. So x to the power y modulo m, right, can just be written as x to the power y by 2 into x to the power, wait a second, let me take this modulo m as well. So we don't have to worry about the number of digits, right? So x to the power y by 2 modulo m into x to the power y by 2 modulo m. And this whole modulo m, right? So when we want to calculate x to the power y modulo m when y is even, we just have to calculate x to the power y by 2 modulo m, calculate this first, right? This is going to take some time. We are just going to, use the same function that we're using to calculate x to the power y modulo m to calculate this number as well. We are going to put the parameters as x, y by 2, and m. This is going to calculate x to the power y 2 modulo m. And whatever this value comes, we're just going to copy paste it here, right? And that will take big O of 1. And then this whole operation is going to take big O of 1. So the time complexity of calculating x to the power y modulo m is nothing but time complexity of calculating this, which is x to the power y by 2 modulo m, right? The second case is when y is odd, right? So how to do like this repeated squaring paradigm when y is odd? So we can still write this in a pretty nice fashion. And here I'm going to use a different color. Let's take green, right? So here the whole equation is going to be x to the power y by 2, and y by 2 is not going to be an integer. It's going to be a fraction here. Above, it was an integer, right? Because y is even, then y by 2 would also be an integer, right? So here we have to take the floor actually to ensure that y by 2, we are powering x by some integer value, right? And not even an integer, just some whole number value, right? And not something which is a fraction, because then the algorithm is going to get a bit messy. So x to the power y by 2 floor modulo m, right, into x to the power y by 2 floor modulo m into x itself, right? So x to the power y by 2 into x to the power y by 2 is just x to the power y by 2 floor into 2, right? And what is this going to become? Is going to become x to the power y minus 1 by 2 into 2, and 2 is by 2 is going to be cancelled. So is x to the power y minus 1. So we are going to multiply x here to ensure that it becomes x to the power y, right? So this is finally going to become x to the power y. So this is the whole equation that we are going to use modulo m, right? So let me clear the part here which I have used to explain this equation, right? So in here, you have to calculate this first, copy paste it here, right? And this whole equation is going to take big of 1, right? Amazing. So we have put our algorithm when y is even and y is odd. Another thing which we have to take care of is when third case, y is 0, right? That is going to be our terminating case. When y is 0, we have to ensure that we just return 1. and don't go into the recursive calling again, because then it's going to get stuck in an infinite loop, right? So here we are just going to code this algorithm, right? Wait a second. Just give me a second. All right. So I'm going to explain how are we doing this algorithm in code. So let me go to my code editor, and then I am going to explain how are we coding this, right? So let me just share my code editor, which is Visual Code Studio. Here, I have already done hashtag include bits std using namespace, standard stuff. We are going to take three integers, x and y and m, and we just want to output some pow m. I'm going to name the function as pow m, right? Capital M, and I'm going to put three integers here, x, y, and m, right? So in this algorithm, the main part was I'm going to return some integer as well, right? Here we take int x, int y, and int m, right? Here, the first part was the base step. In all recursive algorithms, the first part is the base step. And here, the base step is if y is equal to 0, the base step or the terminating case, right? Whatever you want to call that. So if y is equal to 0, then we have to return just 1, because anything to the power 0 is 1. It's like the definition of exponentiation. Anything to the power 0 is 1, 2 to the power 0 is 1, 3 to the power 0 is 1, even 0 to the power 0 is 1, right? That's just a definition that we roll with. So if y is equal to 0, just return 1. Else, what we have to do, let me initialize some int k is equal to pow m of x comma y by 2. In C++, y by 2 automatically gives the floor. So this is going to work in case of odd or even, right? So int k is going to return the x to the power y by 2. Here y by 2 refers to y by 2 floor, right? To m. Now I'm going to separate this into cases. If y is odd, which means y modulo 2 is equal to 1, then we have to return k star x, and to ensure that this doesn't go beyond the um, uh, limits of C++, such that it doesn't overflow, we want to do only two multiplication at a time. So we want to do this multiplication first, which is k star k modulo m, and then we want to do whatever we get the result from here, which is k star k modulo m, and then we want to multiply that by x. That too, I want to return modulo m. But we also want these multiplications to happen in long data type. We don't want this to happen in int data type, because then uh, let's take the left integer as some 10 to the power 9, the right integer is 10 to the power 9. If we multiply these two integers, then the number is going to return in 10 to the power 18, which is of course greater than the int limit C++ has. Int limit in C++ is only less than equal to 2 into 10 to the power 9, right? So we want this to be happening in long data type. That's why I'm multiplying a long one here. It's a short form to typecast any multiplication in long. The explanation of this is 1 ll refers to 1, but in long, right? So 1 ll is nothing but 1. I'm multiplying my whatever number I'm getting by 1, but I'm at the same time typecasting that number in long, right? So 1nl star k, this is going to return k star k modulo m into x modulo m, right? I'm going to return that. Else, if the number is even, that was a simpler case. In that simpler case, I want just 1ll star k modulo m, right? And that is going to be my answer. So let's see if this works or not, right? let's try to see if it is giving correct answer for some big modulos first, right? So let's take 3 to the power 3 modulo some 1000, right? It's giving 27. Let's take 2 to the power 5 modulo some 1000 is giving 32. Let's take if it is giving the correct answers when I'm taking the modulo, right? So 2 to the power 5, but I want the answer to be modulo 30. So 2 to the power 5 is 32, modulo 30 it's going to be 2, so it is returning 2, right? Let's take 27 modulo, let's take 24, right? So 3 to the power 3 modulo 24 should return 3, is returning 3. 3 to the power 3 modulo 26 should be 1, it's returning 1. So this algorithm is working properly without any trouble. Let me also give an example to why this algorithm is working, right? So let me switch to my whiteboard and then I'll give you an example of how does this algorithm work. Wait a second, just okay. So here I have an example: 2 to the power 11 modulo 5 modulo, let's say 7 instead, right? So we want to calculate 2 to the power 11 modulo 7, right? So in the first step, 11 is odd, right? This is odd. So what I'm going to do is reduce this into 2 to the power 5 modulo 7 into 2 to the power 5 modulo 7 into 2 modulo 7, right? And then I'm just going to calculate this. So let me go into this calculation, right? Which is 2 to the power 5 modulo 7. Here as well, this is odd, right? So I have to go to a similar equation, which is 2 to the power 2 modulo 7 into 2 to the power 2 modulo 7 into 2 modulo 7, right? So here as well, here it's 2 to the power 2 modulo 7. Let me go to the calculation of 2 to the power 2 modulo 7. Here, 2 is actually even, right? So we can calculate this in the fashion of just 2 modulo 7 into 2 modulo 7 modulo 7, right? 2 to the power 1 modulo 7, 2 to the power 1 modulo 7. I shouldn't forget the 1, right? So from here, I'm going to again, go to the next step, because this is not the terminating step, right? The terminating step is when my exponent is 0, right? So from here, from 2 to the power 1, I can go to 2 to the power 0 modulo 7 into 2 to the power 0 modulo 7 into 2 modulo 7, right? And here, what you see, this is finally going to be my terminating step, right? If I try to calculate this, which is 2 to the power 0 modulo 7, right? So in here, this is actually 0, and which is my terminating step. So this is actually going to be 1 itself, right? I'm just going to return 1 here. So in this equation, this is going to be 1, and this is going to be 1. So let me try to figure out what this equation would give me. So this equation is going to give me a 1 into 2 modulo 7, which is nothing but 2, right? So 2 to the power 1 modulo 7 is 2, and I'm going to superimpose that here. So this is 2, this is 2. So this is going to become 2 into 2 modulo 7, which is 4, right? So I figured out that 2 to the power 2 modulo 7 is nothing but 4. I'm going to keep that in the above formula as well. So 2 to the power 2 modulo 7 is actually 4. This is going to be 4. So here it's going to be 4 into 2 modulo 7, which is nothing but 16, 32, 32 modulo 7, which is 28. It's going to be 4 again, right? because 7 into 4 is 28 and 32 minus 28 is 4, right? So this is going to be 4. So I figured out that 2 to the power 5 modulo 7 is nothing but 4. And I'm going to keep that in the next equation that I had, which is here. This is going to be 4. This is going to be 4. And again, I'm going to do 4 into 4 into 2 modulo 7. And we know that comes out to be, just 4 itself. So this whole equation is going to be 4. Let's see if 2 to the power 11 modulo 7 actually is 4, right? Let me go to my code editor and compile that again, right? So here 2 to the power 11 modulo 7 is coming out to be 4, which is the answer. If you want to see if it actually works out or not, right? Let me open up my calculator. Let me maximize this and let me share my calculator, right? So 2 to the power 11 is 2048. 2 to the power 10 is 1024. That should be common knowledge. And we multiply our 2 by that, 2048. Let's try to take modulo 7 from that. So 2048 modulo 7 is 4. So calculator is also showing the same thing, right? So this is modular exponentiation, right? And I told you about, I was going to tell you about why are we studying modular exponentiation. The first point was because we don't have to deal with big numbers. The second point is because of this efficient algorithm. Because an efficient algorithm exists. This algorithm is really efficient. I'm going to talk to you about what is a time complexity. But because this efficient algorithm exists, it's used in a lot of problems, right? In many problems, it's directly asked what is not directly asked. It's generally used as a sub problem because this is should be common knowledge, right? So it uses modular exponentiation as a sub problem in the problem, and then you have to use this algorithm to solve that problem, right? So let me go into how efficient this algorithm is. So this algorithm has a space complexity as how many recursive calls it's going to have. So it's going to call from x, y, m to x to the power y by 2m, right? Here floor. Then from there, it's going to call x, y by 2 floor by 2 floor m, right? And this is, it's going to call like this up until it gets to x0m, right? So how many levels are here? At every point, y is getting halved, right? At least halved. At each point, y is getting halved. So the number of levels here is just going to be log m, log y, right? So the space complexity is nothing but big O of log y, right? Time complexity as well. At each recursive call, we are just doing operations of big O of 1. So time complexity is going to be the same as the number of recursive calls, which is also big O of log y. So we have improved from big O of y to big O of log y in terms of time complexity. And in space complexity, we have kind of deteriorated from big O of 1 to big O of log y. But if I have written a recursive for algorithm, if you write an iterative algorithm for the same procedure, then you can actually have a big O of 1 algorithm, right? Just wait a second. Right. Someone has asked it out about the formula that I have written in the code editor. So let me share my code editor first. Right. So he's asking about this line, which is 1 LL into K modulo M into X modulo M. Right. So 1 LL into K. I felt I have explained this pretty properly. I want to typecast this multiplication in long such that integer overflow doesn't happen. Right. That's why I have typecast 1 LL into K. The doubt is we should also write x modulo m, right? So the thing here is x is already in the limits of integers, right? So this is not going to get overflowed, right? So we can write this in the form of x modulo m, right? That is going to be correct as well. But we can write this in the form of only x as well, because that is not going to, generate an integer overflow, right? So we can write this in x modulo m if you prefer, or just x. It doesn't really matter. There isn't going to happen an integer overflow, right? Let's go back to the whiteboard and explain the next topic, which generally comes together with the modular exponentiation. So let me switch to my whiteboard, right? Wait a second. Yes, it's shared to my whiteboard. So let me just revise what I told to you in the last 2 minutes. It was like, this is the recursive algorithm in space complexity. I'm talking about space complexity here, right? Big of 1 is the naive algorithm. This is the efficient recursive algorithm. I've written a recursive algorithm, and it has a space complexity of big of log y. But we can reduce it to a big of 1 space complexity if we write an efficient iterative algorithm, right? Also, this is going to remain big of log y in case of efficient iterative. It isn't going to reduce to big of 1, right? So this is the algorithm with the time complexity of big of log y. This is going to be useful in many sub problems. So try to remember this, where the term by which you can remember this algorithm is repeated squaring, which I told you about here. Wait a second. Let me go back, right? So you can understand the what this term means now. Basically, we are trying to square our number each time, right? Because when we have 2 to the power 0, we square that to 2 to the power 1. Sorry, when we have 2 to the power 1, we square that to 2 to the power 2, right? Then we square that to 2 to the power 4, multiplier 2, get 2 to the power 5. Then we square that number 2 to the power 10, multiplier 2, we get 2 to the power 11, right? So that's what's referred by repeated squaring paradigm. And you can remember this term to remember this algorithm and code this anytime. I would urge you to code this once by your own, because it's really, really important in computer programming, right? This is one of the basics that is taught at many places, right? So this is the whole modular exponentiation. Next, I'm going to go a little deeper and talk about Fermat's little theorem, right? This is generally correlated with the modular exponentiation very often, right? And this is going to be easy as well. And it's more of a concept rather than an algorithm. There isn't really an algorithm, but it is a concept which you should know, right? So what Fermat's little theorem says is simple, right? When the modulo which we are taking, the m, right? If m is prime, if the modulo by which we're taking the number as is prime, and this happens in a lot of computer programming questions, right? If you're seeing some computer programming questions on modular arithmetic, generally they ask you to give the final answer as modulo 10 to the power 9 plus 7. This is a really famous prime number. This is a prime number. That's why they ask you to give it modulo 10 to the power 9 plus 7, such that you can apply Fermat's little theorem. You can apply modular inverse and many other stuff, because modulo some prime number has some really special properties, right? So if m is prime, then Fermat's little theorem states that any x, right? X is from any number, right? Any x, not necessarily containing it in a range. So x to the power m minus 1 modulo m, right? We have understood what this terms means. It's basically modular exponentiation, where exponentiating x to the power of m minus 1 modulo some m, where m is prime, right? This is nothing but 1. It holds for any m that is prime, right? And any x, basically any x. It holds for any x and any m which is prime. X to the power m minus 1 modulo m is 1, right? This is the Fermat-Slidell theorem. The proof is a little advanced. It refers to group theory um, concepts. So you can go to the proof by yourself and try to understand how does this work. The proof isn't going to be very useful in competitive programming though. So the main thing that you have to remember here is this result: x to the power m minus 1 modulo m is equal to 1, right? When m is prime, remember this. You can't apply this algorithm when m isn't prime, right? So what are its uses? Basically, when you're trying to, let's say, calculate x to the power y to the power z modulo m, right? Then you want to calculate y to the power z modulo something, because you don't want y to the power z to have too many digits, right? Because if you try to calculate y to the power z by itself, it is going to have too many digits. That's why you need y to the power z modulo something, right? And what should that something be? That something can be m minus 1, right? Because x to the power y to the power z modulo m is the same as x to the power y to the power z modulo m minus 1 modulo m, right? Because let's say, how does this come out to be from Fermat-Slidell theorem? Let's say x to the power y to the power z. Here y to the power z is actually nothing but y to the power z minus sorry, it's what is the definition of modulo, right? We have to go back to the definition of modulo. Let's erase this. I was going in the wrong direction. Basically, y to the power z is nothing but m minus 1 into y to the power z by m minus 1 floor plus y to the power z modulo m minus 1, right? This is the definition of modulo. What modulo means? It's basically the dividend, or sorry, the divisor. I'm not sure about the divisor versus dividend. I think this is the dividend. Something along those lines. The main parts is this is the quotient and this is the remainder, right? This is basically we're dividing y to the power z by m minus 1, and whatever the remainder comes, it's going to be here. And this is the quotient, this is the divisor. So if we put that in x to the power y to the power z modulo m, right, then it's going to reduce to x to the power y to the power z modulo m minus 1 modulo m, right, into, it's going to result in x to the power m minus 1 into y to the power z by m minus 1 floor, right, modulo m. And as we know from Fermat-Slidell theorem that x to the power m minus 1 modulo m is 1, then this whole number is going to be 1. It's going to reduce to 1 into 1 to the power y to the power z by m minus 1 floor, right, modulo m, which is basically 1, and we are multiplying 1 by something. It's going to be that number itself. So this is going to be this, right? So the final results that comes out of this proof is x to the power y to the power z modulo m is x to the power y to the power z modulo m minus 1 modulo m. That's why if you have to calculate x to the power y to the power z modulo something, you can actually calculate y to the power z modulo m minus 1 first, and then calculate whatever the value you got, x to the power that value, right, modulo m. And that's going to be a lot easier than calculating y to the power z first, because y to the power z can have many digits. So there is another doubt. It's referring to one LL, which I wrote in the code. So let me just take a detour and explain what one LL is. I think I, explained what that was when I was writing the code. But if I haven't, it's basically one typecasted as long, long. Right? Long, long, one. This is the property of C++. It's the syntax of C++. So basically, whenever you type capital L after any number, it just typecasted it into long, long, right? So it's going to have now 8 bytes of memory instead of 4 bytes of memory, right? Because generally when you write a number, let's say you write 2, let's say you write 0, 1, it's generally in the form of int, which is just 4 bytes, right? So after this explanation, let me go to a question to like explain where you can use Fermat's little theorem. So let me share to the web page where I have the problem. And you share subscription overview. Just give me a second. Actually, let me share to whiteboard. A new share onto the subscription overview. Right. All right. So you can see the problem now, which is shopping. Problem code is inlo34. Basically, Shehnaz is fond of shopping and always follows the trend, latest trend in fashion. After completing her high school, she decided to pursue a course in fashion designing. This is the story part. After joining, she realized that the fees of the course was very high and decided to start a side business to pursue her dream. Again, story part. After going through various options, Shehnaz finally decided to run a part-time fashion store from her own room to meet her monthly fees. And there's a lot of story. Low on budget, Shehnaz initially decided to stock up at most one piece of each item for her store. Right? Low on budget, Shehnaz initially decided to stock up at most one piece of each item for her store. She prepared a list of n distinct items that she could use to that she could buy to stock up her store. Can you help her find the number of ways in which she can select at least one item, right? So this is the problem. She has n problems. She's going to stock up on at most one piece of each item. We have to find her the number of ways in which she can select at least one item, right? So the input number of test cases followed by n, which is going to be the number of distinct items, and we have to output the number modulo 10 to the power 9 plus 7. As I told you about, this is a very famous prime number. So we have to modulo output the number of ways modulo 10 to the power 9 plus 7. So if she has two uh, two items, let's say A and B, she can either select A, she can either select B, or she can select both A and B. So she has 3 ways. So 3 here. Let's say she has only one item, right? So that's going to be only A, and the only way in which she can select the items is to select the A item itself, right? So the number of ways is here going to be 1. So let me switch to my whiteboard and explain this problem. This is a really simple problem. You might have understood what we should do here already. Basically, she's going to, if you know a little bit of combinatorics, I'm going to explain it both ways, but if you do know a little bit of combinatorics, there is a combinatorics way. Basically, she can select one item out of the n items. That means she can select nc1 number of ways, right? To select one item out of n items, there are going to be nc1 ways. To select two items out of n items, she's going to have nc2 ways. To select 3 items out of n items, she's going to have nc3 ways, and so on, so on, so on, up until n, right? To select n items out of n items. So this is n choose 1, n choose 2, n choose 3, etc., up until n choose n. So if you do know combinatorics properties and the properties of chooser, right? It's basically that nc0 plus nc1 plus nc2 up until ncn is nothing but 2 to the power n, right? This can be proved by the formula that 1 plus 1 to the power n is nothing but 2 to the power n, right? But let's not go to the formula here. This is the property that we're going to use. Here the NC0 part is missing because she has to select at least one item, right? So we shouldn't include NC0 here. So we are going to do plus NC0 and minus NC0 here. And this is going to return n. Let me scroll my whiteboard. Here it's going to return in 2 to the power n minus NC0, uh, which is 2 to the power n minus 1, right? And we have to model output this modulo 10 to the power 9 plus 7. And that is just going to use modular exponentiation. The other method that I was going to talk to you about is the logic part, right? For each item, let the first item be A, she can either select it or she cannot select it, right? She can either include it in a list or she cannot include it in a list. So there are two ways regarding the item A, right? Let me write this in a better fashion. Two choices regarding item A. Similarly, the next item, B, I can either not select it in my list or I can either select it in my list, right? Similarly, two choices regarding item B, right? Similarly for C, two choices regarding C, etc., etc., etc. So we have basically two choices for each item, but out of all of these choices, one combination is going to be not included, which is when I do not select any item, right? If I choose like A is not going to be on a list, B is not going to be on a list, C is not going to be on a list, such that we go up until n and we do not select, that combination cannot be in our that combination cannot be a possible combination because she has to select at least one item, right? So here, out of the 2 to the power n choices we have, we are going to subtract one, and this is going to be a final answer, modulo 10 to the power 9 plus 7, right? So from either both of these approaches, you are getting to the same formula, which is 2 to the power n minus 1 modulo 10 to the power 9 plus 7, and n is up until 10 to the power 14. So maybe we can modulo that 10 to the power 9 plus 6 first, right? So as to improve the efficiency of our code, right? Because log 10 to the power 14 is greater than log 10 to the power 9 plus 6, right? So let's share my editor and I'll code this algorithm, right? So basically I'm having some test cases int ntc. This is the number of test cases I'm getting, right? In each test cases, I'm getting an n, and it is can be up to 10 to the power 14. That's why I would instead store it in a long data type, because int limit is only up to 2 into 10 to the power 9, right? So C and n, and then what I'm going to do, I'm going to have some int k is equal to power of m. Let's just directly output the answer. We don't have to initialize an int k, right? So power m 2 to the power n to the power modulo 10 to the sorry 1e9 plus 6, right? That's 10 to the power 9 plus 6, comma 1e9 plus 7, right? So we're taking modulo of the exponent by m minus 1, right? That's what we can do by Fermat-Little theorem, right? So n modulo 1e9 plus 6 and 1e9 plus 7. There's an error here. Oh, so 1e9 plus 6 is actually a double. So instead, let's typecast that into integer. That I can do that by 000 000 006, right? So it has 8 zeros, which is what's required. And also here, let's keep 10 to the power 9 plus 7 like this, right? And this is going to be an integer value, not a double value like 1e9 plus 6, right? So this minus 1, and as you know, by modular exponentiation, we shouldn't actually in modular arithmetic, we shouldn't actually subtract something by something, because in C++ that can result in a negative value, and we do not want that. So instead we are going to add this by 1e9 plus 7 minus 1, right? And we are going to take modulo by 1e9 plus 7 at final, right? And we are just going to add a new line character as well. And let's compile this code. Let's see if this works on the sample input output, and then we'll submit for AC. So A1, we have two test cases. First test case is 2, second test case is 1. It's coming out to be 3, 1, right? Let's copy this code and let's share on the web page first. Right, submit this code that I have. And this is most probably going to be AC, right? If it's not AC, it's AC, right? So it's showing up in AC, which means our Fermat-Little theorem and our modular explanation code both are correct, right? So let me next try to make you understand the advanced topics, what you can study after this class, right? What should you cover after this class? What can you learn more in modular exponentiation? So let me go to my whiteboard to explain what advanced topics can you cover here. So we want to generalize the Fermat-Little theorem. That's one of the most popular things in regarding like advanced topics concerning modular exponentiation. So the generalization of Fermat-Little theorem, generalization of Fermat-Little theorem, right? Because what do we want to generalize here? What I mean by generalization, because in Fermat-Little theorem, where x to the power m minus 1 modulo m is equal to 1, here m should be prime, right? But what if it is not prime? So that is refers to the generalization of Fermat-Little theorem. There is one easy generalization, which of which I will just write the result here, right? So an easy generalization is if x and m are co-prime, right? This condition should be satisfied. If x and m are co-prime, basically meaning GCD of x and m are 1 is 1, right? Then we can write the Fermat-Little theorem there as x to the power phi m modulo m is equal to 1, right? Then the form reduces to this. And what is phi m? Phi m is the Euler-Stoichhian function, which is the number of coprimes of m which are less than n, right? Basically, from the range 1 to m, how many coprimes of m exist? That is Euler-Stoichhian function, right? Really easy definition. I get many people get scared from the name, right? Euler-Stoichhian function. It is a rather big name, but the definition is really easy, and like the properties related to Euler-Stoichhian function are also easy. So one generalization is if x and m are co-prime, then we can write the Fermat-Little theorem here as x to the power phi m is modulo m is equal to 1, right? But what if x and m are not co-prime? Then what the generalization should be? That is the hard generalization, which you can like go and read about, and that is something which I can consider like advanced, which can come like when you become master at core forces, or like 5-star or 6-star at core chef, then those questions would become relevant to you. But you can go and study about that right now. I have actually made a problem about the generalization of Fermat Little theorem. Let me share the web page. This is a problem from Code Junk, a contest that I conducted on CodeChef in this year. Code Junk is a like the national signature contest of IIT Guwahati, my college, right? So in here also there is first the logic part that you have to figure out what the answer should be, and then to figure out the answer, to calculate the answer, you have to use a generalization of Fermat Little theorem. And I'm not talking about the easy generalization if x and m are co-prime. I'm talking about the advanced generalization. What if x and m are not co-prime? What if I don't impose any condition on x or m or y, right? So this question is based on that. So if you do intend to study the generalization of Fermat-Little theorem, you can attempt this problem, which is Venkatesh's board of CKOG 20E, right? So you can go attempt this problem. And if there are any doubts related to this lecture currently, you can ask me those. So the two topics that I have told you about that you should go and learn about is the generalization of Fermat-Little theorem, the easy generalization, x and m. And if you want to go a little more advanced, then you can go to the total generalization of Fermat-Little theorem, right? Uh, if there are any doubts currently, you can ask me that, or we are going to end the lecture here. Also, if you do have any doubts unrelated to this topic, or some doubts that are a little personal, you can ask me on like Code Forces or Code Chef. You can message me there and just ask me there itself, right? My handle at Code Forces is Zeus Ors, or my handle at Code Chef is NM, right? So you can go there, message me, and I will try to get your doubt sorted. Any doubts relevant to this topic, or any doubts that you want to ask me? Uh, so you can just write it around the chat and I'll answer them. NCR modulo M, right? So one person has asked me about NCR modulo M, right? So this is a concept which comes after modular exponentiation, right? Because NCR, as you guys which have learned combinatorics, combination and permutation, NCR is nothing but n factorial by r factorial into n minus r factorial, right? So here n factorial we can calculate in modular arithmetic easily. 1 into 2 into 3 into up until n. It is going to be the naive algorithm. But how do we calculate by r factorial, n minus r by factorial, in like dividing these numbers, right? So it's something like n factorial into r factorial inverse into n minus r factorial inverse whole modulo m, right? So in here, you have to use the concept of modular inverse, right? So there is a concept of in modular arithmetics, first the basics of modular arithmetic, then the modular exponentiation, which I have taught you in this class. And then there's the final concept, which is modular inverse. It is in my number 3 course under Academy. I will also try to take a free class on that. So it, finally concludes the modular arithmetic basics, and finally shows you how to calculate NCR modulo M, in which you have to know about how to use modular inverse. That is also one of the basics in computer programming, and you should know how to calculate modular inverse, because NCR is going to be prevalent in most of the probability questions that is going to be asked in computer programming. So you should know how to calculate NCR, and for that you have to study about modular inverse, right? It's easy. It's comparatively easy. If you do know about the Fermat Little theorem, then it's just really basic on how to calculate modular inverse, but you should go and study about that. Then x to the power y to the power z can be written as x to the power m minus 1 into x to the power m minus 1 q times xr, where r is the first q terms will be equal to 1 by Fermat's Little theorem. So we just need to calculate. Yeah, right. How FMT is used in this? How Fermat Little theorem is used in the problem that I solved? It isn't actually. I'm going to be honest. That problem doesn't use Fermat Little theorem that efficiently, right? I have basically just the n I was getting, and I have to calculate 2 to the power n. So instead of calculate 2 to the power n, I have calculated 2 to the power n modulo m minus 1, right? But I could have calculated in that question to the power m directly as well, right? Instead of having my function in int only, I could have typecasted my function in long, and then I could have calculated to the power m. That would have taken me a time complexity of big of log 10 to the power 14, and this takes me a time complexity of big of log 10 to the power 9, right? Because m is around 10 to the power 9. There isn't a much difference between these two, so this doesn't really improve my uh, uh, complexity that well. But you certainly can find problems which deal with Fermat Little theorem, like which are better than this, which absolutely require Fermat Little theorem. uh, Without Fermat Little theorem you cannot solve that problem. There are problems certainly about that. You can go to code chef and sort by tag number theory, and you will come across problems if you try to solve all of them, right? So just go to codechef.com. Let me actually show you how to do that. New share onto my web page. So if you go to codechef.com, you can go to search problem by tags, right? And in here, when you search number theory, actually let me sort by problem count. So in here, there is this number theory where there are 89 questions. So you can go directly to number theory. And here there will be all of the problems based on number theory. If you want to practice based on just modular arithmetic, you can actually go to modular arithmetic here. And there are many problems based on modular arithmetic as well. So you can go and solve those. Let's say y to the power z. Just wait a second. Let's say y to the power z is equal to q star m minus 1 plus r. Oh, that's the explanation part. Sorry. So any other doubts related to this topic? So if not, let me just close this lecture. And also, if you do have any doubts other than the doubts discussed here, you can ask me on my handles, which is use or code forces or nm at code chef. Also, there is a feedback form in the description box. So please do fill that feedback form, as it helps me to understand how like how am I teaching, how fast am I going, how slow am I going. You can go like this video, subscribe to this channel, because there are going to be many videos coming out, not only by me, by other people as well, which are really informative, right? So do like and subscribe and go down and fill the feedback form. That is really important, so that I can gauge where do I how to improve myself currently, right? So thank you for attending this lecture. This was me talking about modular exponentiation. Uh, if possible, the next scheduled free class is on Unacademy. It's going to be on dynamic programming, on game theory, as well as probability. So you can do attend that. It is going to be on the 13th of October, right? So meet you on there. And for right now, bye. And I hope that you learned something from this lecture. Okay, bye.